In this module, we are going to look at the AWS core services. First up, Amazon Virtual Private Cloud, or VPC. The AWS Cloud offers pay-as-you-go, on-demand compute and managed services, all accessible via the web. These compute resources and services must be accessible via normal IP protocols implemented with familiar network structures. Customers need to adhere to networking best practices and meet regulatory and organizational requirements. Amazon Virtual Private Cloud, or VPC, is a networking AWS service that you will need to meet your networking requirements. Amazon Virtual Private Cloud, or VPC, allows you to create a private network within the AWS cloud that uses many of the same concepts as an on-premise network. But much of the complexity of setting up a network has been abstracted without sacrificing control, security, and usability. Amazon Virtual Private Cloud, or VPC, also gives you complete control of the network configuration. You can define normal networking configuration items such as IP addresses, subnets, and routing tables. This allows you to control what you expose to the internet and what you isolate within the Amazon VPC. Amazon VPC builds upon the AWS global infrastructure of regions and AZs and allows you to easily take advantage of the high availability provided by the AWS cloud. It also allows you to provision virtual networks hosted on the AWS cloud dedicated to your AWS account. When you create a VPC, it will span across all the AZs of a single region. Each AWS account can create multiple VPCs that can be used to segregate environments. A VPC defines an IP address space that is then divided by subnets. VPCs are logically isolated from each other. You can create many subnets in a VPC, though fewer is recommended to limit the complexity of the network topology. But this is totally up to you. You can configure route tables for your subnets to control the traffic between subnets and the internet. By default, all subnets within a VPC can communicate with each other. Subnets are generally classified as public or private, with public having direct access to the internet and private not having direct access to the internet. For a subnet to be public, you need to attach an internet gateway to the VPC and update the route table of the public subnet to send non-local traffic to the internet gateway. Amazon Elastic Compute Cloud, or EC2 instances, also must have a public IP address to route to an internet gateway. Let's design an Amazon VPC that you can start deploying compute resources and AWS services. We will create a network that supports high availability and uses multiple subnets. First, because VPC is region-based, you need to select a region, say the Singapore region. Next, you will need to create a VPC. Let's name it Test VPC, and you will define the IP address space for the VPC. The 10.0.0.0/16 is the classless inter-domain routing, or CIDR format, and means that you have over 65,000 IP addresses to use in the VPC. Next, you will create a subnet named Subnet A1. You have assigned an IP address space that contains 256 IP addresses, and this subnet will live in AZ-A. Next, you will create another subnet called Subnet B1 and assign it an IP address space, however, this time with 512 IP addresses. For the non-networking administrators in the audience, there are plenty of CIDR calculators online that can help you figure out the number of IP addresses in a CIDR range. We have added an internet gateway called Test IGW. Subnet A1 will become a public subnet where workloads can be directly accessed from the internet. Subnet B1 will be your private subnet that is isolated from the internet. For the network administrators in the audience, you may find the network design diagram somewhat familiar. This is because the public subnet will map nicely to your DMZ, and the private subnet will map to your production network in an on-premises environment. Let's summarize what you have learned so far and review some next steps. You have learned about VPCs, internet gateways, and subnets. Next steps in your future learning include other VPC features such as routing tables, VPC endpoints, and peering connections. Also, you can learn about deploying AWS resources into your VPC. Let's take a look at AWS security groups. Security of the AWS cloud is one of our highest priorities, and there are many robust security options to help you secure your data in the AWS cloud. One of the features is security groups. At AWS, security groups act like a built-in Layer 4 firewall for your virtual servers. With these security groups, you have full control on how accessible your instances are. At the most basic level, it is just another method to filter traffic to your instances. To determine who has access to your instances, you would configure a security group rule. Rules can vary from keeping the instance completely private, totally public, or somewhere in between. Here's an example of a classic AWS multi-tier security group. In this architecture, notice multiple different security group rules have been created to accommodate this multi-tiered web architecture. If you start at the web tier, there is a rule set up to accept traffic from anywhere on the internet on port 80 and 443 by selecting the source of 0.0.0.0/0. Next, if you move to the app tier, there is a security group that only accepts traffic from the web tier. And similarly, the database tier can only accept traffic from the app tier. Finally, there has also been a rule created to allow administration remotely from the corporate network over SSH port 22. The security group configurations follows the least privilege principle, where the access is limited to those that need it and no more than that. We now move on to the next core service, compute. Data centers are expensive to build, staff, and maintain. Hardware are purchased often based upon projected plans, not actual usage. You need to provision resources for the worst case. Your servers must be able to handle traffic spikes and events. Unfortunately, after the build-out, you often have capacity lying idle. AWS offers flexibility and cost effectiveness. With AWS, you can scale your compute needs to your workload. Scalability is built into our compute services so that as demand increases, you can easily scale up. If demand drops, say, at night or on weekends, you can scale down to save money and resources. You don't need to pay for what you are not using. Computing needs may change over time, and our Amazon EC2 service, for example, offers a wide variety of instance types appropriate from simple web servers to large machine learning clusters. You are not locked into specific hardware configurations that you have purchased and can easily change instance types. Amazon EC2 allows you complete flexibility to run applications at any scale. You maintain complete control over your environment, and unlike an on-premises environment with on-demand pricing, you can cost-effectively scale resources up and down to meet your needs. What if, instead of running servers, you could just run your application when needed? AWS Lambda lets you run code without provisioning or manage servers. You pay only for the compute time you consume. There is no charge when your code is not running. With Lambda, you can run code for virtually any type of application or backend service: mobile, Internet of Things, IoT, streaming services, and more, all with zero administration. For example, say I want to process an uploaded image. I can upload the image to Amazon Simple Storage Service, or S3, which is a service that allows you to store and retrieve any amount of data from anywhere, and use an event trigger to launch a Lambda function to process the image without having to have an idle server standing by. Think about it, the ease of running compute without having to provision and maintain servers. It's like switching on a light and not having to think about how the power is generated and sent to your home. A great example of utility computing. If you need to run a simple website or e-commerce applications, AWS offers Amazon Lightsail. With Lightsail, you can launch a virtual private server in just minutes and easily manage simple web and application servers. Lightsail includes everything needed to jumpstart your project: a virtual machine, SSD-based storage, data transfer, DNS management, and a static IP address for a low, predictable price. Do you use container services on premises? Amazon Elastic Container Service, Amazon ECS, is a highly scalable, high-performance container management service that supports Docker containers and allows you to easily run applications on a managed cluster of Amazon EC2 instances. Amazon ECS eliminates the need for you to install, operate, and scale your own cluster management infrastructure. AWS Fargate is a technology for Amazon ECS that allows users to run containers without having to manage servers or clusters. It removes the need to interact or think about servers or clusters. Amazon EKS, or Amazon Elastic Container Service for Kubernetes, is a managed service that makes it simple to run Kubernetes on AWS without needing to install or operate your own Kubernetes clusters. Kubernetes is an open source platform that is used for managing containerized applications and workloads. Wow, now that's a lot of compute services to take in. Let's focus on Amazon EC2 that underpins many of the workload that you will be deploying on the AWS platform. First, why is it called Amazon EC2, which stands for Amazon Elastic Compute Cloud? Well, compute refers to the server resources that are being presented. There's a lot of different fun and exciting things you can do with servers, as you can see from the list of server types on the right of the screen. Cloud refers to the fact that these are cloud-hosted compute resources. Elastic refers to the fact that if properly configured, you can increase or decrease the amount of servers required by an application automatically, according to the current demands on that application. But let's stop calling them servers and use the proper name of Amazon EC2 instances. Instances are pay-as-you-go. You pay for running instances and for the time they are running. Provided with Amazon EC2 instances, are the broad selection of hardware and software and selection of where to host your instances. If you have been using any kind of hypervisor on premises, an EC2 instance is conceptually similar to a virtual machine. There are many different families of instance types, as you can see from the table above. They are in turn grouped into different broad categories for different use cases, like compute optimized to be used for science and engineering apps, or GPU optimized for machine learning. Here in AWS, we are constantly innovating and pushing out new instance types and newer versions of existing instance types so that you, our customer, benefits from these latest technologies available from our technology partner, Intel. All of the EC2 instances are powered by Intel Xeon processors. And by using Amazon EC2 instances, you have quicker access to the various Intel compute innovation at a click of a button. All you need to do to change or upgrade your EC2 instance hardware is to stop it, pick the instance type and size you want, and start it up. The ease of accessing different EC2 instance types and sizes allow you to use a larger compute resource to complete your job quicker and save you money because you can deprovision it once your job is done. This table shows you for each family of instance type the Intel technology that is supported. Do check out the AWS EC2 product page for the latest information as it gets updated regularly. C5 instances are designed for compute-heavy applications like batch processing, distributed analytics, high-performance computing, ad serving, highly scalable multiplayer gaming, and video encoding. The new instances offer a 25% price-performance improvement over C4 instances, with over 50% for some workloads. They also have additional memory per vCPU, and for code that can make use of the new AVX 512 instructions twice the performance for vector and floating point workloads. Over the years, we have been working non-stop to provide our customers with the best possible networking, storage, and compute performance, with a long-term focus on offloading many types of work to dedicated hardware designed and built by AWS. The C5 instance type incorporates the latest generation of our hardware offloads and also takes another big step forward with the addition of a new hypervisor that runs hand-in-glove with our hardware. The new hypervisor allows us to give you access to all of the processing power provided by the host hardware while also making performance even more consistent and further raising the bar on security. The general purpose M instances go all the way back to 2006 when we launched the M1.small. We continued to evolve along this branch of our family tree, launching the M2 in 2009, M3 in 2012, and M4 in 2015. Our customers use the general purpose instances to run web and app servers, host enterprise applications, support online games, just about any kind of workload you can think of. Currently, M5 instances are the next generation of Amazon EC2 general purpose instances, powered by 2.5 GHz Intel Xeon Platinum 8000 series processors, with enhanced networking and a new larger instance size that provides up to 96 vCPUs and 384 gigabytes of memory. M5 instances have up to 50% more vCPUs and memory and 25% more network bandwidth than M4. With all of that compute power, you are going to need to distribute it. Yes? In comes Elastic Load Balancing, or ELB. Elastic Load Balancing, ELB, is a managed load balancing service that distributes incoming application traffic across multiple Amazon EC2 instances. There are currently 3 product offerings: the Application Load Balancer, or ALB, Network Load Balancer, or NLB, and the Classic Load Balancer. Here's a table that broadly compares these 3 types of load balancers. First up is the Application Load Balancer, ALB, that functions at the application level. It supports content-based routing and applications that run in containers. It supports a pair of industry-standard protocols, WebSocket and HTTP2, and can provide additional visibility into the health of the target instances and containers. Then you have Network Load Balancer, NLB, which is designed to handle tens of millions of requests per second while maintaining high throughput at ultra-low latency. Rounding up the pack is a Classic Load Balancer, CLB, that provides the basic load balancing across multiple Amazon EC2 instances and operates at both requests and connection level. We recommend the using of ALB or NLB for workloads running in VPCs. Do check out the Elastic Load Balancing product page for more details and side-by-side comparisons. Application Load Balancer can be used in many scenarios. One is the ability to use containers to host your microservices and route to those applications from a single load balancer. Application Load Balancer allows you to route different requests to the same instance but defer the path based on the port. If you have different containers listening on various ports, you can set up routing rules to distribute traffic to only the desired backend application. Here, you can see how the Application Load Balancer routes and organizes backend targets. While configuring a listeners for the load balancer, you create rules to direct how the request received by the load balancer will be routed to the backend targets. To register those targets to the load balancer and configure the health check the load balancer will use for the targets, you create target groups. Targets can also be members of multiple target groups. Depending on how your backend is designed, targets can be either EC2 instances or containers. NLB is optimized to handle sudden and volatile traffic patterns while using a single static IP address per AZ. Because it can handle millions of requests per second while maintaining ultra-low latencies, it is ideal for the applications that require extreme performance. And to complete the compute conversation, we will now touch on auto-scaling. Auto-scaling assists you with designing the desired number of Amazon EC2 instances you want to handle the load for your application. Using auto-scaling removes the guesswork of how many EC2 instances you must have at a point in time to meet your workload requirements. When you run your applications on EC2 instances, it is critical to monitor the performance of your workload using Amazon CloudWatch. CloudWatch by itself, however, will not add or remove EC2 instances. This is where auto-scaling comes into the picture. With Amazon EC2 auto-scaling, you can maintain the health and availability of your fleet. Also dynamically scale your EC2 instances to meet demands during spikes and lulls. Let's look at an example workload. You could use CloudWatch to measure EC2 resource requirements over a standard week. Note that the resource requirements vary, with Wednesday requiring the most capacity and Saturday the least. If you allocate enough EC2 capacity to handle your highest demand time, in this case Wednesday, it means that you are over-provisioning most of the week. This is not a cost-optimized option. On the other hand, you could allocate fewer EC2 instances, thus reducing costs. This could mean that you are under capacity on certain days. And if you don't solve your capacity problem, your application could underperform or potentially even time out for your user. Auto-scaling allows you to add or remove EC2 instances based on conditions that you specify. Auto-scaling is especially powerful in environments with fluctuating performance requirements. This allows you to maintain performance and minimize costs. So auto-scaling really answers two critical questions. How can I make sure that my workload has enough EC2 resources to meet fluctuating performance requirements? And how can EC2 resource provisioning occur on demand? Auto-scaling matches up with two AWS best practices. Make your environment scalable and automate as much as possible. Let's take a look at auto-scaling a little closer. So what exactly is meant by scaling? The first thing you have to do is define the conditions for scaling out and scaling in. Auto-scaling can automatically adjust the number of EC2 instances running in your workload based on either conditions that you defined, for example, CPU utilization over 80%, or a schedule. If auto-scaling adds more instances, this is termed scaling out. This is represented by the middle diagram where the ELB is load balancing 3 EC2 instances. The instance highlighted by the green box represents the third instance added to the auto-scaling group compared to the base configuration. As auto-scaling terminates instances, this is an example of scaling in. This is represented by the diagram on the right, where one of the instances has been terminated, resulting in only 2 instances in the auto-scaling group. Remember that you have control as to what initiates these events. So, how do you automatically scale? There are 3 components required for auto-scaling. First, you create a launch configuration. Second, you create an auto-scaling group. And finally, you define at least one auto-scaling policy. Let's take a closer look at what each of these components do. A launch configuration defines what will be launched by auto-scaling. Think of all the things that you would specify when you launch an EC2 instance from the console. These include which Amazon machine image to use, what instance type, security groups, or roles to apply to the instance. What is an auto-scaling group? This is about defining where the deployment takes place and some boundaries for the deployment. This is where you define which VPC and subnets to deploy instances, which load balancer to interact with. You also specify the boundaries for a group. If you set a minimum of 2 and your server count goes below 2, another instance will be launched to replace it. If you set the maximum of 8, there will never be more than 8 instances in your group. The desired capacity is the number of EC2 instances that you want now. Lastly, what is an auto-scaling policy? This is about specifying when to launch or terminate EC2 instances. You can schedule auto-scaling every Thursday at 3 p.m., for example, or create conditions, if met, to trigger adding or removing instances. Condition-based policies make your auto-scaling dynamic and can meet fluctuating requirements. It is best practice to create at least one auto-scaling policy to specify when to scale out, and at least one policy to specify when to scale in. So how does dynamic auto-scaling work? One common configuration is to create CloudWatch alarms based on performance information from your EC2 instances or a load balancer. As a performance threshold is breached, a CloudWatch alarm triggers an auto-scaling event which either scales out or scales in EC2 instances in the environment. Briefly, CloudWatch is a monitoring service used to collect performance statistics like EC2 instance CPU utilization and turn them into matrices to be monitored. For example, if you are monitoring CPU utilization of an EC2 instance using CloudWatch and have an alarm set to trigger if the utilization is set above 60%. If the alarm is triggered, CloudWatch will execute the auto-scaling policy to add one or more EC2 instances to the auto-scaling group. Auto-scaling will inform ELB to register the new EC2 instance and start sending requests to it. The same principle applies for scaling in. The first part of the alarm is a condition with a specific threshold. In this case, CPU utilization is greater than 80%. Note there is also a time period specified that you can control. This means you could be specifying that the alarm will fire up if CPU utilization is over 80% for 5 consecutive minutes. The time period is critical because you don't want auto-scaling to trigger new instances because your processor spiked for 30 seconds. The second part of the alarm is the action to perform after the alarm is triggered. With auto-scaling, the action could be to add or remove instances. So in this example, if the CPU is over 80% for one consecutive period, 5 minutes by default, auto-scaling will add 2 new instances to the auto-scaling group. When you add more instances, the CPU utilization should go down. You should set another CloudWatch alarm to define a threshold as to when instances should be terminated from the auto-scaling group. As an example, as CPU utilization goes below 20% for more than 5 consecutive minutes, terminate one instance. The beauty of it all is that auto-scaling can manage your workload dynamically so you do not have to focus on it. Let's summarize what you have learned. Auto-scaling allows you to add or remove EC2 instances based on conditions that you specify. Auto-scaling is especially powerful in environments with fluctuating performance requirements. This allows you to maintain performance and minimize costs. Best of all, this process can scale in or out EC2 instances in the middle of the night while you are sleeping. The 3 core components you must have are a launch configuration, what you like to deploy, an auto-scaling group, where you would like to deploy, and an auto-scaling policy, when you would like to deploy. Remember, every AWS service that you learned about is another tool to build solutions. Now, into one of my favorite topics, storage. And first up is Amazon Elastic Block Store, or EBS. Think of Amazon Elastic Block Store, or EBS volumes, as an actual hard drive that can be used as a storage unit for your Amazon EC2 instance. So whenever you think you must have disk space for your instances running on AWS, you can use them. These volumes can be hard drive or SSD devices, and you pay as you use them. So whenever you don't need a volume anymore, you can just delete it. Amazon Elastic Block Store, or EBS volumes, are designed for being durable and available. This means that the data in a volume is automatically replicated across multiple servers running in the AZ. I made a comparison about EBS volumes and physical media devices like hard drives or SSDs for the ease of understanding. But it's actually more durable than that because of the block-level replication. While creating an EBS volume, you can select the type of storage that best fits your needs. You can choose between magnetic or SSD based on your performance and price requirements. It is all about choosing the right tool for the right job. So for example, if you're running a database instance, you can configure the database to use a secondary volume using SSD for data, which may perform faster than the volume assigned to the operating system. Or you can assign a magnetic volume for the logs because magnetic is cheaper. To provide an even higher level of data durability, Amazon EBS gives you the ability to create point-in-time snapshots of your volumes, and AWS allows you to recreate a new volume from a snapshot at any time. Share or even copy snapshots to different AWS regions for even greater disaster recovery protection. You can, for example, share your snapshots from the Singapore to the Tokyo region. You can also have encrypted EBS volumes at no additional costs. The encryption occurs on the EC2 side, so the data moving between the EC2 instance and the EBS volume inside AWS data centers will be encrypted in transit. When your company grows, the amount of data stored on your EBS volumes will probably also grow. EBS volumes have the ability to increase capacity and change to different types, meaning that you can change from hard drive to SSD or increase from a 50 gigabyte volume to a 16 terabyte volume. And this resizing operation can be done on the fly without having to stop the instances. And that's it. In summary, we have reviewed what EBS volumes are and its various characteristics. We will next take a look at one of our oldest AWS service, Amazon Simple Storage Service, or S3. Amazon Simple Storage Service, or S3, is a fully managed storage service that provides a simple API for storing and retrieving data. You don't have to manage any infrastructure yourself and can put as many objects into S3 as you want. S3 holds trillions of objects and regularly peaks at millions of requests per second. Objects can be almost any data file, such as images, videos, or server logs. S3 supports objects as large as 5 terabytes in size. You could even store database snapshots as objects. Amazon S3 also provides low latency access to the data over the internet by HTTP or HTTPS, so you can retrieve data anytime, anywhere. You can also access S3 privately through a virtual private cloud endpoint. You get fine-grained control over who can access your data using identity and access management, or IAM policies, S3 bucket policies, and even per-object access control lists. By default, none of your data is shared publicly. You can also encrypt your data in transit and choose to enable server-side encryption on your objects. Let's take a file that needs to be stored in S3, such as a welcome video. First, you have to create a bucket whose name must be globally unique in Amazon S3 service. This is because the bucket name is used to form a unique URL that you can use to access the bucket. When you want to put this welcome video into the bucket as an object, you can do so by uploading it into the bucket via the management console with a click of a button. The name of the file, welcome.mp4, is now the key that you will reference as part of the URL to access the actual object in the S3 bucket. The sample URL has been color-coded to highlight where the bucket name and key come together to form a unique URL used to access the video. You can access S3 by the Management Console, AWS CLI, or AWS SDK. Additionally, you can also access the data in your bucket directly via REST endpoints. These support HTTP or HTTPS access. This flexibility to store virtually unlimited amount of data and access that data from anywhere makes the S3 service suitable for a wide range of scenarios. As a location for any application data, S3 buckets provide that shared location for storing objects that any instance of your application can access, including applications on EC2 instances or on-premises servers. This can be useful for user-generated media files, server logs, or other files your application needs to store in a common location. Also, because the content can be fetched directly over the web, you can offload serving that content from your application and allow clients to directly fetch the data themselves from S3. For static web hosting, S3 buckets can serve up the static content of your website, including HTML, CSS, JavaScript, and other files. S3 is designed for 11 nines of durability, which makes it a good candidate to store backups of your data. For even greater availability and disaster recovery capability, S3 can even be configured to support cross-region replication such that data put into an S3 bucket in one region can be automatically replicated to another S3 region. The scalable storage and performance of S3 make it a great candidate for staging or long-term storage of data you plan to analyze using a variety of big data tools. In summary, we have taken a quick look at Amazon S3, touched on some of its characteristics like high durability, accessibility, security controls, and some common use cases. Right, so now we're going to log in using a demo user called S3 Demo into the AWS Management Console. Once in, we're going to click on the S3 icon in the navigation bar at the top of the page, which will drop us into the Amazon S3 console. Now I'm going to create a bucket using S3 Demo as a name, and I'm going to drop it in the Singapore region, leaving everything else as default. When I try to click the Create button, it gives me an error message saying that the bucket name already exists. Now, it really doesn't matter which region I select now, because the bucket name must be unique across the AWS infrastructure. So I'm going to change the name to something else. And I'm going to still select the Singapore region. As you can see, it is now successfully created. Next, I'm going to upload an object into this demo bucket. Clicking on Upload, Add Files, and I'll select a file randomly from my laptop. And this happens to be an image. And I'll click on Upload, and it now appears in my bucket. Selecting the Tiger JPEG, I can see that this particular object has a unique URL which I can select and try to access it. But as you can see, I receive an access denied error message because by default, all buckets are not public. I can very easily make this particular image publicly accessible by clicking the Make Public button and refreshing that same tab. You will now see the image I've uploaded. That ends the very short and simple demonstration of creating S3 bucket and uploading an object. We shift gears now and look at different AWS database services. Coming up is Amazon Relational Database Service, or RDS. Let's first take a look at the challenges of running a standalone relational database. As you run your own database, you are responsible for several administrative tasks like server maintenance, OS and software installation, as well as patching, backups, ensuring high availability, scalability, planning, and data security. All these tasks take resources away from other items on your to-do list and requires expertise in several areas. To address the challenges that come with running your own relational database, AWS provides a service that sets up, operates, and scales the relational database without any ongoing administration. Amazon Relational Database Service, or RDS, provides cost-efficient and resizable capacity while automating time-consuming administrative tasks like the ones we have previously covered. Amazon Relational Database Service, or RDS, frees you to focus on your application, so you can give them the performance, high availability, security, and compatibility they must have. With Amazon RDS, your primary focus becomes your data and optimizing your application. Amazon RDS manages operating system installation and patching, database software installation and patching, automatic backups, and high availability. Scaling resources, managing power and servers, and performing maintenance is also covered by AWS. In short, all of the undifferentiated heavy lifting is offloaded to managed Amazon RDS service, reducing your operational workload and the costs associated with your relational database. Now let's go through a brief overview of the service and a few potential use cases. The basic building block of Amazon RDS is the database instance. A database instance is an isolated database environment that can contain multiple user-created databases and can be accessed by using the same tools and applications that you use with a standalone database server. The resources found in the database instance can be determined by its database instance class, and the type of storage is dictated by the type of drives. Database instances and storage differ in performance characteristics and price, allowing you to tailor your performance and costs to the needs of your database. When you choose to create a database instance, you first have to specify which database engine to run. Amazon RDS currently supports 6 database engines: MySQL, Amazon Aurora, Microsoft SQL Server, PostgreSQL, MariaDB, and Oracle. You deploy an Amazon RDS instance in a VPC of your choice, giving you control over your virtual networking environment. One of the most powerful features of Amazon RDS is the ability to configure your database instance for high availability with a multi-AZ deployment. After configuration, Amazon RDS automatically generates a standby copy of the database instance in another AZ within the same Amazon VPC. After seeding the database copy, transactions are synchronously replicated to the standby copy. Running a database instance with multi-AZ can enhance availability during planned system maintenance and help protect your databases against database instance failure and AZ disruptions. If the master database instance fails, Amazon RDS automatically brings the standby database instance online as the new master. Due to the synchronous replication, there should be no data loss. As the applications refer the database by name using RDS DNS endpoint, you don't have to change anything in your application code to use the standby copy for failover. Amazon RDS also supports the creation of read replicas for MySQL, MariaDB, PostgreSQL, and Amazon Aurora. Updates made to the source database instance are asynchronously copied to the read replica instance. You can reduce the load on your source database instance by routing read queries from applications to the read replica. Using read replicas, you can also scale out beyond the capacity constraints of a single database instance for read-heavy database workloads. Read replicas can also be promoted to become the master database instance. But because of the asynchronous replication, this requires manual action. Read replicas can be created in a different region as a new master database. This feature can help satisfy disaster recovery requirements or cutting down on latency by directing reads to a read replica closer to the user. Amazon RDS supports the most demanding database applications. You can choose between two SSD-backed storage options, one optimized for high-performance OLTP applications, and the other for cost-effective general-purpose use. With Amazon RDS, you can scale your database compute and storage resources with no downtime and use the AWS Management Console, the Amazon RDS command line, or simple API calls to manage the service. Amazon RDS runs on the same highly reliable infrastructure used by other AWS services. It also lets you run your database instances in your VPC, which provides you with control and security. Now let's take a look at a managed NoSQL database service, Amazon DynamoDB. Amazon DynamoDB is a fully managed NoSQL non-relational database service. AWS manages all of the underlying data infrastructure for this service and redundantly stores data across multiple facilities within a region as part of the fault-tolerant architecture. With DynamoDB, you can create tables and items. You can add items to a table. For the DB administrators out there, an item in a DynamoDB table is similar to a row in the RDBMS table. The DynamoDB service automatically partitions your table and has table storage to meet the workload requirements with no practical limit on the number of items you can store in a table. Some customers have production tables that contain billions of items. One of the benefits of a NoSQL database is that items in the same table may have different attributes. This gives you the flexibility to add attributes as your application evolves. You can have newer format items stored side by side with older format items in the same table without having to perform schema migrations. Again, for the DB administrators out there, attributes in DynamoDB are similar to columns in an RDBMS table. As your application becomes more popular and as users continue to interact with it, the DynamoDB table can grow with your application needs. All of the data in DynamoDB is stored on solid-state drives, and a simple query language allows for consistent, low-latency query performance. In addition to scaling storage, DynamoDB also allows you to provision the amount of read or write throughput you have for your table. When the number of application users grow, DynamoDB tables can be manually scaled to handle the increased number of reads and writes requests with manual provisioning. Alternatively, you can enable auto-scaling so DynamoDB monitors the load on the table and automatically increases or decreases the provision throughput. Some additional key differentiating features include global tables that enables you to automatically replicate across your choice of AWS regions, encryption at rest, and item TTL. The ability to scale your tables in terms of both storage and provision throughput makes Amazon DynamoDB a good fit for structured data from the web, mobile, and Internet of Things applications. For instance, you may have a large number of clients continuously generating data and making large numbers of requests per second. In this case, the throughput scaling of DynamoDB allows consistent performance for your clients. DynamoDB is also used in latency-sensitive applications. The predictable query performance, even in large tables, makes it useful for cases where variable latency could cause significant impact to the user experience or to business goals such as ad tech or gaming. Table data is partitioned and indexed by primary key. There are two ways of retrieving data from a DynamoDB table. The first method is the query operation that takes advantage of the partitioning to effectively locate items by using the primary key. The second method is via a scan, which will allow you to locate items in the table by matching conditions on non-key attributes. The second method gives you flexibility to locate items by other attributes. However, the operation is less efficient as DynamoDB will scan through all the items in the table to find the ones that match your criteria. To take full advantage of query operations and DynamoDB, it's important to think about the key you use to uniquely identify items in a DynamoDB table. You can set up a simple primary key based on a single attribute of the data values with a uniform distribution, such as the GUID or other random identifiers. For example, if you were to model a table with products, you could use some attributes, such as the product ID, that would be the table on the left. Alternatively, you can specify a compound key, which would be composed of a partition key and a sort key. That would be the table on the right. In this example, if I was to have a table on songs, I might use the combination of song title and singer to uniquely identify table items. In summary, Amazon DynamoDB is a managed NoSQL database service which can be used as a data store for applications which need to scale to store large amounts of data, support high request volume, and require low latency query performance. We have come to the end of Module 2. Test your knowledge with the following questions.